This is Dr. Indradeep Kumar, Assistant Professor, IARE, Hyderabad. So in this video, we will see another derivation for torsion of an arbitrary section beam. Right. So our lecture topic is derivation for torsion of an arbitrary section beam. Now we will go for another derivation. So let's see. This is the question. Right. Prove that 2AR equals to 2AR comma naught minus integral of C 2AR comma naught into TDS by integral of C TDS for a thin walled arbitrary section beam under torsion where T is the thickness. So this we have to prove. 2AR equals to 2AR naught minus integral of C 2AR naught TDS by integral of C, that is of the cross section, into TDS. This we have to prove. Okay, so let's start the solution. So as we had seen that from what we are starting, sigma t, then the integral form of this one, doing the same way we can do, and in that previous video also I told the similar way from the same derivation you can derive 3 to 4 derivation as well as the question. So let's see here. So in the presence of axial constraint d theta by dz is no longer constant, so that the longitudinal strain del w by del z is not 0. Now what happened? D theta by dz is now not constant, and if it's not constant, is what? The longitudinal strain del w by del z is also not 0. Why? Longitudinal strain, because now del theta d theta by dz is changing, so the strain also will be there. That is no, that means del w by del z is not 0. Some value will be there, and direct and shear stresses are induced. Means now direct and shear stress also will be there. Why? Because d theta by dz is not constant. If d theta by dz is there, then del w by del z in already in previous derivation we had seen that becomes 0, and there is no direct stresses are there. So here once this starts changing, means the other things also like longitudinal strain, direct stress and shear stress, these things are getting changed. So already this we had seen that sigma tau equals to E del W by del Z. Right. So after putting the value of del W that we had seen, what was W? W equals to minus 2AR. Okay. 2AR into d theta by dz. So this was W. Now what we are doing, we are differentiating because we require del W by del Z. So let's differentiate this one. So now this will be, I'm writing here, del W by del Z, okay, equals to minus 2AR remains constant, so minus 2AR, and now d theta differentiation of this d theta by dz becomes d2 theta by dz square. Right. So now just substituted this value here for this del W by del Z. So now this becomes E into this value. So E into this value. So it becomes minus 2AR E into d theta by dz square. Right. So now this is our sigma tau. The sigma tau stress system must be self-equilibrating since the applied load is pure torque. Now what happened? That must be self-equilibrating. Means what? They should come to the equilibrium, or they should maintain the equilibrium by their self only. Why? Because here only the pure torque is up there. Right. Applied load is a pure torque. There is no other load or anything is there. Only what we are considering that as pure torque. Hence, they must, what? Should be self-equilibrating. Right? Therefore, at an section, the resultant in load is 0. So, it's a pure torque is the other load. Definitely, the resultant of other load must be 0. Why? Because of this self-equilibrating in nature. So, just if all the forces at the end section, that is 0. So, just equate to 0. So, how much total forces will be there? What is the force formula? Force is what? The stress into area. Right. Sigma is just here. So force, that is, this is F equals to sigma T, that is the stress into TDS is area. So the stress into area, right, from here, that must be equals to 0. So this we can say the force is 0. So integral of C denotes what? Integration around the beam section. Means this C represent here integration around the beam section. Or from equation 1 and observing that d2 theta by dz square is a function of z only, right? d2 theta by dz square is a function of z only, means and 2AR TDS, right? 2AR, after putting here 2AR TDS, because here we required in terms of ds, so d2 theta by dz square now here is the function of z, hence that is constant, it's not a function of s. Meaning what? So from here, after putting this value, so what we will get? Let's see. Here I am putting this value. So what we required for c, integral of c, sigma tau. Sigma tau is this one. So minus 2AR e into d2 theta by dz square. This into TDS. Into TDS. Right. Now, what is it that this d2 theta by dz square is a function of z, means hence here it is constant. Why? Because this integration is the function of s. Means here ds is there, s is changing, not z is changing. So means this is constant. Right. Take out of that integration. So now this will be what? Minus also I am taking out. So minus d2 theta by dz square. Okay, out of integral c. Now this is 2AR into TDS. That equals to 0 from here after substituting. Now take this side. So after this what we will get? Goes to that integral of c 2AR into TDS equals to 0 by minus d2 theta by dz square. So 0 by something, again that will be 0. Hence this equals to 0, and that is here. Okay. So now integral c 2AR TDS equals to 0. Okay. So now this we have 2AR TDS equals to 0. The limit of integration of equation 2 represents some difficulties in that AR is 0 when W is 0. So now earlier also we discussed that taking limit here is difficult. So what to take the limit? So for that only, what is that? That AR is 0 when W is 0. So when wrapping is 0 means AR will be 0 at an unknown value of S. Though even whatever the value of S is there, if AR will be 0 when wrapping will be 0. Okay. So now let's see. So from this figure earlier also, that's why that time also I told that many times this, if you remember this image, 3-4 derivation you can use with that one. One more video that in next video we will see to find the rate of twist. In the rate of twist again the same figure is required. There you have to find by what rate, that is d theta by dz we have to find. So how much rate will be there, that d theta by dz, there we find, there also we will use the same thing. So as like earlier, so when s is 0, that is starting from here, right? And so area swept up to this, like up to once it's s is becomes s equals to s simply. So up to s, right? Here that is there. So this is area, right? AR, this total area internal before this one, right? Now at s equals to 0 when wrapping is 0, so this is up to this part only is there when W is 0. So this, that's why you can see here this is a straight line first, right? Like this, and over this one this line is there like this. So this part is half of this one, right? So inside one is how much? Inner one total from here to here is AR, and from here to here is AR dash. Then what will be this remaining area? That what is this area, right? So this area will be what? AR minus AR dash, right? Because this is total AR, right? And this is AR dash. So what we can write that as AR, this is AR, right? So AR will be there. So see here. So this part is AR. So we have to find AR. So AR will be equals to what? AR is equals to this part is this whole. This whole is what? AR naught. AR comma naught. When wrapping is 0, this is the full area. Minus how much? This part. Right. So that is AR dash. Now, because in our formula 2 is there, so just multiply 2, or because of that, in another word you can say because of the symmetry also. So now this will be 2AR equals to 2AR naught minus A dash R. So this should be the area, right, from figure 1. So just see 2AR equals to 2AR naught minus 2A dash R. Okay, so now this A we have. Now here what we have to do, just find the value of A dash R, because this is already known. So this, once we will have this 2AR dash value, we can substitute, and that will be the final equation for 2AR. Okay, so let's see here, where AR 0 is the area swept out from S equals to 0. So from S equals to 0, and AR dash is the value of AR naught at W equals to 0. So what is AR? 2AR dash when wrapping is 0. So that is the value of AR naught at W equals to 0. This when wrapping is 0, that time AR naught, what is the value of AR naught is there? That will be the what? AR dash. Mr. C once again, where AR is the area swept out from S equals to 0. So from S equals to 0 it's starting, and totally this area is forming from here to here. That is like this area is AR naught. So this total area. Now when wrapping is there, so instead of in that time, instead of covering the full area, only when W becomes 0, up to that only they will sweep the area. And that's why their name is, when that W is 0, that will be AR naught. So this at W equals to 0, whatever the value of AR naught will be there. So let's see once again, at W equals to 0, or when W is 0, that time, right, whatever the value of AR naught will be there, right, that is this line, that will be equals to A dash R. Clear? So when wrapping is 0, so here wrapping is 0 means this value, that area swept value will be 2AR. Okay. So next, let's see. Then in equation 2, now just integrate both sides after substituting here. 2AR equals to 2AR naught minus 2AR dash. This is 2AR value. So now from here in equation 2, right, put that value. So instead of 2AR, so I am just writing here. So what we have, close integral C for 2AR, what is that? For this 2AR I am writing. 2AR is 2A dash R minus, 2AR naught minus 2AR dash. This is the value of 2AR into T ds. Right, this is the value just here. Yeah, 2AR is 2AR naught minus 2A dash R. Right? So after substituting this one, now what happened? This is in terms of minus. So let's multiply first this one. So after multiplying the first term, what we will get? Integral of C. I'm just first multiplying. So 2AR naught T ds. And then this minus sign, 2A dash R into T ds. Right, this one. So now instead of that, we are just making this just separating by using integral property. Means now this we can write integral C 2AR comma naught T ds and minus integral C 2A dash R T ds. Okay, so now these 2 is there. Right, so just separate it. So that is here. Let's see. Integral C 2AR naught into T ds minus 2AR dash, because 2AR dash is constant. So out of the integration, integral T ds, that is equals to 0. So that is equals to 0. Okay. So now here. Okay. So now from here what we will do? Just we have to find 2AR dash. So in this case what can we do? What we can do? Just take this to this side. So from here we can write integral C, right, 2AR comma 0 into T ds is equals to 2A dash R into C, that integral C T ds. Right, after taking this to this side, this is minus, so that side it becomes plus. This is them. Now what we have to find? 2AR dash. So keep 2AR dash and this will come to this side. Right. So now 2AR dash or 2A dash R is equals to what? Integral of C 2AR comma 0 TDS whole divided by this term. Integral of C TDS. The C that we got. 2AR dash is equals to integral C of 2AR comma naught T into TDS. TDS is area, remember. We are seeing. Okay, so sigma tau into TDS. So that TDS is here. Divided by integral C of TDS. Now, just substitute this 2AR dash value where in equation that is here. So now substitute this value to here. Okay. So now after substituting, what we will get? Simply 2AR equals to 2AR comma naught minus this whole thing, that is integral of C 2AR comma 0 or comma naught TDS by integral C of TDS. So now finally we got this equation, and that only, let's see that what is that? That only we have to derive. 2AR equals to 2AR comma naught integral C 2AR comma naught TDS by integral C of TDS. That only we have to derive. So now we derived. Right. So this figure is very important. With this figure, once you know this area value, we can derive 2, not 3 and 4 derivation. With this only we can solve by this figure and some other figure. Like in next video also we will see where we have to find the rate of twist. In that also we will use the same figure to find the rate of twist, because area swept is required. Area swept under the wrapping condition, when that is load is 0, that time what happened? When wrapping becomes 0, then what happened? So by those conditions we can find the other derivation also. So that is important, this one. And that next video, earlier also we had seen the same figure. In this next video also we will see the same figure, right? And another figure also will be there, but this will help to find the 2AR value. Okay, so let me recall quickly once. So just see, this time question is just numerical type, that prove that 2AR equals to 2AR comma naught minus integral of C 2AR comma C TDS by integral C TDS. This we have to derive. That is given in the question itself. Earlier whatever the just condition is there and then we derive. But here this time directly they given the equation that we have to derive. Right. And the condition also is given for arbitrary section beam under torsion. So here torsion load is applying, means no other loads are there, means purely torsion or purely torque is only applied. All other load, that is 0. So same here, what happened in the presence of axial constraint. Now once we will put the axial constraint like that one, that time d theta by dz is not constant. Now that becomes variable, that will also change. Why? So, and once d theta by dz will change, this strain will also there. Strain won't be 0, because here d theta by dz is constant. That's why longitudinal strain was 0. But now d theta by dz is not 0. So means longitudinal strain is not 0. It will have some value, and direct and shear stress also will be there. Means direct and shear stress will also induced, means they will have some value, not in the case of d theta by dz, because when d theta by dz is constant, that time del w by del z there is no longitudinal strain, there is no direct stress, right? But here once d theta by dz will change, means all other things will be there. So now what will be there? So in this case first we have to find what? Shear stress. That stress we require to find, because here the stress will induced. So stress is what? Sigma t equals to E into del W by del Z. That del W formula, you know, the W equals to what? Minus 2AR into d theta by dz. Right? What we require? dW by del W by del Z. Means we have to differentiate this one. So after differentiating, what we will get? d2 theta by dz square. Right? So that is here. Right? So now we have what? Sigma T. Right? The sigma T stress system must be self-equilibrating. Why? Because early in the question itself, though that time I told you that there is no other load, only the pure torque is applied. Hence, all the resultant. If suppose any load is there, then also that is not affecting, only because of the torque they have the twist or torsion, right? So means all the forces must be equal to the sum of that, or resultant of all the forces must be equals to 0. So that is here the resultant of all the forces is equals to 0, because force is what? Stress into area. So stress we found, and this is area, so that must be equals to 0 over the entire beam. So that's why here it's mentioned that integration around the beam section. So now in this equation, just substitute the value of what? Sigma tau. So sigma tau is this one, right? After substituting sigma tau here, right? And what will be the next condition? d2 theta by dz square, because in this equation now ds is variable, not the dz is variable. So d2 theta by dz square will be what? Constant. In this case, that won't be constant because this is varying, hence stress will induced. But now when we will integrate with respect to s, means del s, that time this will be constant. So now this is constant, taking out of the integration, that minus d2 theta by dz square. So inside it will be what? Minus 2ARE. E also constants out of integration into TDS. So now E d2 theta by dz square will come this side, 0 by E d2 theta by dz square, that also 0. So finally you will get what? C equals to 2AR TDS, that is equals to 0. Now, so again we will use this equation. In this equation only we will put the 2AR value. So for that, next figure is required. So here is the figure. In that I explained, this is starting from s equals to 0 and it's forming, right, that area swept. So this is A, this inner one, total, this AR naught. Okay. Now, when it's a start and wrapping is 0, that at the time of wrapping, this same AR naught, okay, will be equals to what? AR. That's just we assume, because we cannot take the same thing. So for when AR is there and W is there, that wrapping is there, then they will form this one. Once the wrapping will be 0, then only whatever the value of AR naught will be there, that is the AR dash. Right? So just here, this is the equation. Just substitute this equation in the previous equation here, that is here after expanding. Now, just this is equals to 0 as 4. So take this to this side. So now this term is equals to this term. So from here 2AR dash will be equals to this. Now substitute this 2AR dash in this equation. So now what we will get? 2AR equals to 2AR comma naught minus 2A dash R by, sorry, minus this whole thing, integral C 2AR comma 0 TDS by integral of C TDS. That is here. So finally the derivation over. Okay. In next video we will see again related to the same figure, but another difference. The difference will be there in the derivation. Okay. That rate of twist. Right. So I just see it's written here, the center of twist. Right. R. So there we will find this is the center of the twist point. But in the next video we will find the rate of twist, that is called d theta by dz. How to derive the equation for that one. Okay. Actually for the next video this is there. So just skip this one. Later we will see. Right. So this is this one, and here this is the reference again. The Maxen book is there that you can refer. So if you have any doubt or anything, you just comment on the video or you can contact me regarding your doubt. I will clarify the doubt. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.